Welcome to week 8 of case studies in scientific literacy and the final and fourth lecture in the climate change module. So we have covered quite a bit in only 3 hours so far. We talked about Earth's climate system, some natural drivers of climate change or global change, and anthropogenic drivers of climate change. So this week we are going to talk about what does the future hold? What are the predictions about the future and climate change? Some climate models, how do we get those predictions? And then I'm going to talk about some impacts of climate change that are happening already and that are predicted to happen in the future. And then what can we do about it? We as in humankind, and then very briefly, we as in individuals. Okay, so you may have seen the hockey stick prediction with temperature skyrocketing, out to 2100. Or you may have seen maps like this showing temperature increase out to 2100 over the whole globe. But how do scientists come up with these predictions? We hope that they're not using a crystal ball to come up with those predictions. How do they do that? Well, they use climate models. And these climate models predict greenhouse gas emissions as well as total concentration in the atmosphere, and then from that they can predict other things like temperature. So I'm going to tell you a little bit about these climate models so that when you hear about them you know vaguely what they might be about. We could spend, of course, an entire semester talking about climate models. So they're usually called general circulation models or global circulation models, and they basically simulate the effects of greenhouse gases sometime into the future. And what the scientists do, or the people who do these models, they set up this huge grid system over the Earth. These grids are 100 to 200 kilometers in size, and then they model mathematically the movement of mass as well as energy between those cells. So they're similar to models that are used to predict the weather, but on a much broader scale in terms of geography, but temporally as well. So they're predicting hundreds of years into the future. We don't predict weather hundreds of years into the future. So this, I just wanted to show you that these grid cells go far up into the atmosphere, but they are also going down into the oceans. So these models now include the oceans as well. And again, they're modeling movement of mass and energy between those cells. Now, the resolution of global climate models has greatly increased. So the grid cells are getting smaller and smaller. And the reason for that is that our computing power is getting greater, for one thing, and our understanding of how mass and energy move in the atmosphere and the ocean is also getting better. So, if we had tried to run these models on a computer, like a laptop, it would be running for decades probably, right? But now we have these massive computers that can run things much more quickly, because obviously it gets really complicated. So another way to look at how they've kind of come along is that they started out in the mid-70s and all they could model was the atmosphere. And then they started including the land surface. Remember, the reflectivity is important. And then they started adding in the ocean and the sea ice, which is also important. Then they started adding in the carbon cycle and aerosols and so on. So over the years, these climate models have gotten much more sophisticated. So they used to be, we still generally call them global circulation models or general circulation models, then atmosphere oceanic models, and now a lot of times, because now they include things like vegetation, which is important in modeling, atmospheric chemistry and so on. Now they're often called Earth system models. So you'll probably see that I often just shorten them to GCMs. So there are a variety of these GCMs that are done by a whole suite of institutions. And this is just a few of them. There are probably dozens that are done by different groups of people. And they differ in the way that they model those interactions of mass and energy between the grid cells. So they often come up with similar answers, but maybe somewhat different because of how they model those processes. So here's just some examples of the sort of most common models. There's one out of the UK. There's one done in Colorado, Canada. NASA does one. Australia does one. So these are common institutions that do the GCMs, or global climate models. And again, they differ in how they treat the interactions and the various processes. So they can also, not only do individual institutions differ in how they model, but we can look at different emission scenarios. So if, say, we stopped using fossil fuels entirely, what will happen? Or if we keep using fossil fuels as we are now, what will happen? So they make assumptions about how much greenhouse gases will be produced in the future based on different scenarios that are produced by this institution called IPCC, which I'll talk about next. So the IPCC is the Intergovernmental Panel on Climate Change, which you may or may not have heard of. It was established in 1988 as with two organizations together, the World Meteorological Organization and the United Nations Environmental Program. And it now has, last I checked, 195 member governments are part of this panel. And in fact, in 2007, the IPCC shared the Nobel Peace Prize with Al Gore for climate change. So what this panel does is it gathers all this information about global change, and it reviews and assesses that information. And one of the many things that it does is it produces these sort of standard scenarios of greenhouse gas emissions for use in these climate change models. So what are these standard scenarios? We start with the basic 4 scenarios. And they kind of go by, we have the A's and B's. So A's are more where the world has economic priorities. The B's are more where we have environmental priorities. Then the 1's are where we have more global priorities, and the B's are where we're more interested in sort of regional, local development. So if we look at these, for example, A1, moderate population increase, high tech advancement, which might be good for reducing fossil fuels, right? Global convergence on living standards. So that means that we'll actually be using more energy because we're going to bring up people now who are using very little energy. B2 might be slow economic growth, low population growth, focus on environmental sustainability, regional solutions to environmental problems as opposed to global. So these are the 4 kind of basic scenarios that they have come up with. And from there, they've got subfamilies and so on of different scenarios. So for example, here we have our A1, they call them storylines, A1 family, and then one of these might be where we use a lot of fossil fuels to meet our energy needs. One might be where we use alternative energies to meet our energy needs. And one might be where we're kind of balanced between fossil fuel use and alternative energies, and so on. So then these institutions that do models take these different scenarios and run them based on kind of how much fossil fuels those different scenarios might use. So here's the one out of Australia, for example, and they've got, you know, the A1 balanced, A1 alternative fuels, A1 fossil fuels, and so on. And you can see that different scenarios of population growth and economic development and so on end up producing different amounts of CO2. Makes sense, right? And then based on that, how much CO2 might be in the atmosphere from what we're producing under these different scenarios. So another thing I wanted to point out is that all of these have some error associated with them. So these, the pink or the light green and so on, is one standard deviation if you have done statistics. But what I want to point out is as we go further out in time, that error gets bigger, for one thing. So I took out a slide that now I wish I'd left in. So last year, January 2016, there was a big blizzard in the Northeast, right? And the weather people were so excited. There's like a picture of Jim Cantor, like, yay! He was so excited because they actually predicted what would happen, like the amount, the flooding, the timing, where it would be, and they were so excited about that. So even, you know, short-term predictions, they're not always right, right? So there's definitely some error associated, especially when you're going out 100 years, right? Okay, so then those models, once they've predicted greenhouse gas emissions or CO2 emissions and CO2 concentration in the atmosphere, then they can predict things like what will the global temperature be like 100 years from now. So they produce things like this. Okay, so this is showing temperature change out. Let's see, let's do it again. Okay. It's not showing, somehow it's not showing the years. Is it? Anyway, you get the idea. They can do things like this. Okay. So they can, with these models, then they can go and do predictions for not only temperature rise, like that previous slide, but how much will the oceans warm? How much will sea level rise? Will there be extreme events? Sea ice. Can we expect there to be no Arctic sea ice? So things like this, they can now model based on those predictions of CO2. So what does the future hold? The predictions show rising temperatures, lengthening growing seasons. So there's a whole suite of things we could talk about. I'm going to talk about just a few of them. Lengthening growing season, changes in precipitation, droughts as a result of that, heat waves, more intense hurricanes, rising sea level, an ice-free Arctic at some point. So I'm just going to go through a few of these, well, actually most of them, I think, except ice-free Arctic. So temperature projections. So here we have 2020 to 2029 and out further, out to 2099. And we see a couple of things. First off, that the Arctic is going to warm a lot more than the rest of the globe. So these are under different scenarios, B1, A1, B, balanced, A2, and so on. So you can see that under different emission scenarios, we get more warming or less warming. The other thing that this graph shows is that in the short term, we're more, the probability of those things happening is better. And in the longer, if we go out to the longer term, our error is greater. So some things are already happening. This is observed increase in frost-free season. So basically how long is summer between last spring frost and the first fall frost. And already between 1958 and 2012, some areas have increased that frost-free season by almost 20 days already. What does it look like in the future? So predicted frost-free days for 2070 to 2099. And this is the change in days, so increase in number of frost-free days. And you can see that especially in the West, the number of frost-free days is going to greatly increase. The white areas are places that will have no frost ever. Okay, Miami, we usually don't have frost anyway, but the gray areas are areas that will have no frost for 10 years running, but may have frosts sometimes. So that has implications for a lot of things. And since we're in IFAS, I'm going to kind of concentrate on, agriculture and things like that. Decreased yield for a lot of reasons, because things like heat stress, weeds and diseases that require a frost to kind of knock them back, right? And freeze vulnerability. So if we don't have freezes for 10 years running and then we have one, imagine what that does to tree crops and so on like that. Precipitation. We have already had changes in precipitation patterns. So this is 1991 to 2012 compared to earlier in the century. And we can already see that there's been an increase in precipitation in the Midwest, decrease in precipitation in the Southwest. And what does the future look like? So this is modeled for if emissions continue to increase. So 2070 to 2099 compared to earlier, and we see that precipitation will increase in some areas, decrease in others, and it will change more in the winter and spring than in fall and summer. Droughts, drought projection by 2100. So some places will experience a lot of drought. And these are probably the same places that really can't afford to have droughts, right? And in fact, I just saw this from Cornell University. Mega droughts, so those that last 35 years or more, the American Southwest likely will rise from a low chance over the past 1,000 years to a 20 to 50% chance in this century of having a mega drought. And with changes in temperature, changes in frost-free days, changes in precipitation, increased drought, we also get biome shifts. So over time, the natural plants and habitats are going to shift. So, for example, one of the things we see is up here we see a lot more dry grassland as opposed to temperate forest. We see increased savanna up here, and so on. So those are going to have some pretty big consequences. There will also be changes in crop yields as a result. So this is for out to 2050, and we can see some places crop yields may actually increase. They're going to get more rain and so on. But in a lot of places, crop yields could change or decrease by 50%. And if we look at one country in particular, so this is the change in potential cereal output in 2080. And we see that, again, some places might actually experience an increase in crop yields, but many places will experience decreases of 5 to as much as 50% decrease in crop yields. So imagine not just the ecological impacts of shifting biomes, but the social and political and human health aspects of not producing enough food. So to kind of segue into the next or the last session in this course, GMOs. Maybe, are we going to need GMOs in order to feed the world? And again, here's one that came up just recently. Even if the Paris Agreement is implemented, food and water supplies remain at risk. And we may see, major crops declining in these sort of breadbasket areas where people might be starving. And I threw this in, malaria as an example, but there are many diseases that as climate shifts, these diseases are going to expand into places they have never been before. So malaria is an example. Maybe we're going to have malaria here in Florida. And so that kind of goes into your next session, vaccines. With spreading diseases, are we going to need vaccines to prevent disease outbreaks? Okay, so let's see. We've talked about up to droughts. How about heat waves? So heat waves, or this does it by number of days above 100 degrees. So under different scenarios, for example, the Great Plains and the Midwest are predicted to have many more days over 100 degrees. And predicted increases in heat-related deaths just in Chicago, under different scenarios are expected to increase. So these actually are heat waves that we've already had that killed people in Chicago, 2006, 1999. A bunch of people died in 1995. So that one is actually similar to the B1 emission scenario. But if we have, for example, the A2 emission scenario, we can expect people to die in these heat waves. And that has, again, human health implications, obviously. Population migrations, are people going to just move away from places that are uncomfortable? And again, this one just came up. Heat increases risk for farm labor. So heat waves will have implications for so many things. Our energy use, we all have air conditioners, so we run our air conditioners so that we stay cool. But many people don't have access to that. It will impact our agriculture, so many things. And again, we could spend tons of time talking about all these different potential impacts. Hurricanes. Will hurricanes increase? So this is one that, there's a lot of different data. Some suggest that hurricanes numbers will increase. Others suggest that hurricane intensity will increase. This one suggests that as sea surface temperatures rise, which they are, the number of hurricanes might not increase, but the intensity of those hurricanes will increase. So we'll see more hurricanes moving into the category 5 and fewer in the lower categories. Sea level rise. I'm not going to play this one because this is a Colbert report, so you guys can watch that later. It's really funny. If you haven't, have you guys seen this one before? Sink or swim. It's really good. Okay, so we won't watch that. But you may have seen these sort of doomsday scenarios, right, where all of Florida is underwater. Colbert has one where, in that video, Florida is underwater. You may have seen these. So what's the reality? The reality is that different scenarios or different models under different emission scenarios have a pretty wide range of what they're predicting, anywhere from a quarter of a meter global sea level rise to 2 meters of sea level rise by 2100. So whatever it is, say it's a meter, 5 million people just in the US live below 4 feet sea level, basically. So that many people will be without homes if sea level rises 4 feet. Energy facilities, almost 300 energy facilities, are also lower than that because they use cooling water from the ocean. So, these things are a concern. Again, population migration. Where are we going to get energy if our energy plants are inundated? Okay, so the next question is, what can we do? So the Framework Convention on Climate Change has a goal, which basically is to prevent dangerous human interference in the climate system. Stabilization of greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous interference with the climate system. Such a level should be achieved within a time sufficient to allow ecosystems to adapt naturally. I think we might be too late for that one. To ensure that food production is not threatened, and to enable economic development to proceed in a sustainable manner. So I teach a course on natural resources in a changing climate, so we talk about this in that class. But let's look at the stabilization of greenhouse gases. There's a lot of discussion on what that means. What does it mean to stabilize greenhouse gases? One is to prevent change from exceeding a 2-degree temperature change, and the target would be under 400 parts per million greenhouse gases. Oops, I think we already got that right. The next one is to stabilize greenhouse gases at about double what it was pre-industrial. So about 550, 500 parts per million. Okay. Another strategy that has been talked about is called the overshoot strategy, and that's actually to allow greenhouse gases to exceed, to rise above the target, and then later sometime we'll bring it back down when we have the technological advances to do that or the political will to do that, because maybe we don't right now. Okay. Yeah, so we've already exceeded this one, right? And in fact, I forgot to sub that. This guy from NOAA says, it's unlikely we'll ever see CO2 below 400 parts per million during our lifetimes, probably much longer. So the last time the Earth had 400 parts per million was 3 million years ago. During most of our evolution, we've been at around 278. So we've kind of already, got past that one. And I think last week we had a question about, have we kind of passed the point of no return? Because 400 was kind of set as that no return point. And scientists, don't agree on whether we have hit a point of no return. But there are certainly sort of reinforcing positive feedbacks that are going to be hard to get out of. Will there be a really rapid climate change to some new stable? I don't know that we can predict that. So let's look at this stabilizing at about 400 parts per million. Since we've missed this one, and this one doesn't seem like a really great idea, let's look at this one. So how could we do that? So what can be done to stabilize greenhouse gases? Well, we can reduce emissions. So we use a lot of energy, right? There are many ways that we could conserve energy as a society and as individuals. We could be a lot more energy efficient. So even just, the power lines outside, we're losing energy. It's very energy inefficient. We could also use alternative energies other than fossil fuels. We could also offset emissions so we could keep using fossil fuels, know that we're going to produce CO2, and offset those emissions by sequestering that carbon. So I'm going to talk a little bit about these alternative energies. And how much of this are we going to have to do to keep it below the 500 parts per million? So you may have seen graphs like this, in which this is fossil fuel emissions if we kind of do the business as usual approach. And this is trying to stabilize CO2 at 500 parts per million. So we would actually need to, as time goes on, we'll need to decrease our fossil fuel emissions. So that's stabilizing at 500 parts per million. And the difference between business as usual and trying to stabilize at 500 parts per million is called a stabilization triangle. And that represents about 175 gigatons of carbon emissions. Now, it's often broken down into little wedges. They're called stabilization wedges, usually 7 of them, of 25 gigatons of carbon, because somehow it's easier to think of 25 than some big number, I don't know. Or 1 gigaton of carbon per year for the next 50 years. So we're going to have to come up with some way of finding enough energy that doesn't produce fossil fuel if we want to keep doing business as usual in terms of our society and energy use, but keep emissions down, we have to find some other way of getting that energy, right? So alternative energies come in. So can we find solutions that have the potential to provide these wedges? So we have things like we could maybe do a wedge that by being more efficient and conserving energy, we might be able to do wedges by sequestering carbon, or we might be able to do some wedges by using some alternative fuels to reduce or offset emissions. So I'm going to go through some of these energy sources because each of them has costs and benefits. So solar. One wedge would require about 2 million hectares of stuff out in the sun, which actually isn't a lot. It's not that much. But they're often put in deserts, for example, that have underestimated biodiversity. We think, oh, there's nothing there, but really there is. It might be far away from population centers, so then you have to move the energy from there to where the people are. So it has some detractors also. Wind. One wedge would require about 30 million hectares. This is a picture that I took along the Columbia River. I was in Oregon, and these are in Washington. And so you can co-locate these. So there could be animals grazing here. So just because it takes up 30 million hectares, it doesn't really, maybe. But a lot of people don't like to see these. So they're maybe aesthetically not pleasing. They do kill birds. They also put them oftentimes in they stand in the ocean. And when they're drilling them, they have a big impact on marine mammals. So wind power also has some costs associated with it. Biofuels. So one wedge would require about 250 million hectares, representing about 17% of our agricultural land. That's a lot. And in fact, in many countries, biofuels is already contributing to deforestation. Not good, right? Competition with food production, increased fertilizer use, which will then increase dead zones in the Gulf of Mexico, and so on. So there are costs associated with biofuels as well. Hydropower. So one wedge would only require about 2 to 3 million hectares. In the temperate zones of the world, there's actually not that many more rivers that we could dam. In the tropics, dams or the reservoirs behind dams are actually net emitters of greenhouse gases because vegetation gets into them and is eaten up by bacteria, producing methane and CO2. So they're net emitters of greenhouse gases. And of course, if you're going to flood new areas, especially in the tropics, you're going to impact other organisms like these parrots in Belize, which really happened. Geothermal. Sounds like a great idea. Probably can't even support one wedge because there's so few places in the world where we could actually do it on a big scale. But on a small scale, people can do this. For example, my brother built a house and he's got uses geothermal to both heat and cool his house using these pipes that go into the ground because the ground is always the same temperature, right? So on an individual basis, we could do this, but probably on a Big scale, not so much. Nuclear is relatively compact. One wedge would only require 700,000 hectares. But this is not a growing industry because of safety and environmental concerns. You know, concerns about accidents, what do we do with the waste, and so on. So this, while many countries do have, like France has a lot of their power coming from nuclear, but in a lot of parts of the world, this is not a growing sector. But so it may require kind of all of these together to help provide these wedges of stabilization. How about emissions, offsetting emissions by carbon sequestration? So a lot of ideas about carbon sequestration have been floated. Maybe that's kind of a pun I didn't actually intend. So capturing CO2 and injecting it into deep oceans, fertilizing the oceans so that we get phytoplankton blooms. That stuff uses up CO2, falls to the bottom, taking the carbon with it. Free air sequestration is basically technology for removing CO2 out of the air, turning it into a solid that would no longer be, contributing to the atmosphere. And basically, those two have kind of been busted. They'd have a lot of problems associated with them, including increasing ocean acidification. The free air sequestration is plausible. The technology isn't there yet. There's some prototypes out there, but so far it's not economically feasible. But certainly biomass sequestration is something that we can do. So where deforestation has taken place, we can reforest. And those trees represent a lot of carbon. Where there are not trees, we could plant trees. We can manage the forests we have to sequester more carbon. That's another class. Soil has a lot of carbon in it, and we can manage our soil and the soil microbes and our crops to keep more carbon in it. Wetlands hold a lot of carbon. The peat, the plants have a lot of carbon, and so wetland restoration, wetland management can contribute to sequestering more carbon. One of my favorites, use of wood products. So instead of using cement or metal building products, if we use wood to build something that has an indefinite lifetime, we're sequestering carbon. So one of my favorite things now, I say, I'm buying a book, I'm sequestering carbon. Okay, so what can we do? We can, yes?
But if we start using a lot of wood products, wouldn't that just cut back into deforestation?
Well, but most of the wood products now, if you look for the little sustainable label, they are planted purposefully to grow a tree for a product, right? So it is real, it really is, and they're managed, like they're almost like micromanaged, so they're managed to be sustainable. So unless you're clear cutting, forest in the Amazon or something, I think it is sequestering carbon. It is sustainable. So we can use alternative fuels. We can sequester carbon. But those are kind of things on a, society-wide scale. Are we going to contribute individually to a wedge? Probably not. But there are small things that we can do. So there's a lot of these carbon, like calculate your carbon footprint. So you can, here's one, for example, that you can go to. It asks you, where you live, how much you fly, do you eat meat, things like that, and it kind of calculates how much carbon emissions you as an individual produce. And it gives you an idea of where you could cut back. So, my kids, when they were little, they watched Bob the Builder a lot. Maybe you guys don't know Bob the Builder, but reduce, reuse, recycle, right? So those are some ways that we, in a very, very tiny wedge, could reduce our carbon emissions, right? So reduce everything that you use, recycle. No, okay, I'm gonna have a confession here. Like, most of what I'm wearing came from a consignment or thrift store. It's recycling, right? So no new carbon was used in producing my clothes. Somebody else paid for it the first time. So there's a lot of little things that we can think about as we live our lives. We're not going to make a huge impact individually, of course, but maybe as a whole we can. Okay, so that was the last of our climate change module. Next up, I believe, is GMOs. So you'll talk about what those are. And finally, the last part of the class is vaccines. So we covered a lot in only 4 hours. I had a really good time putting this together, and I hope that you guys had a good time and know more about climate change than you did when we started, so that if you took those quizzes again, you would know more than that first time. Okay.